The Great Red Spot on the planet Jupiter is the largest storm on any planet in the entire solar system. In the past, it was even bigger than now. The sheer depth of it is hard to grasp. To give you an idea, it's like having around 45 Mariana Trenches stacked on top of each other. On Earth, hurricanes quickly lose their strength when moving over land, but on Jupiter, there is no land, and so there isn't any friction to slow down the massive storm. It's been raging for centuries, but it looks like something strange is happening to the Great Red Spot. Since the late 19th century, it has shrunk significantly, evolving in size, shape, and even color. From its origins as a vast oval over 3 times the width of Earth to its present dimensions, approximately 10,000 miles wide, the Great Red Spot storm has taken on more of a circular shape, while its colors have been ranging from pale to intense red-orange hues. Scientists believe chemicals like ammonia and hydrocarbons in Jupiter's upper layers might be responsible for these colors, but the exact mechanisms remain unclear. But no matter how majestic, the Great Red Spot is just one fascinating feature of the gas giant Jupiter. Jupiter's atmosphere is a swirling mix of belts, zones, and cyclones, with strong east-west winds separating the distinctive cloud bands. It makes up only 1% of the planet's mass, but it's very intricate, and the processes behind its peculiar features aren't completely clear yet. The giant gas planet is famous for its jet streams, or relatively stable winds. Some of them reach speeds of 320 miles per hour, are over 3,000 miles wide, and extend more than 1,850 miles below the planet's clouds. It would seem that when comparing Jupiter and Earth, they are 2 entirely different planets in every way you look at them. But surprisingly, there's something uniting the 2 worlds. When scientists studied the chemicals present in Jupiter's atmosphere, they noticed an abundance of ammonia and its puzzling distribution. Some regions have much higher concentrations, and there are even ammonia columns extending from deep within Jupiter and up to its top cloud layers. Using data from NASA's Juno spacecraft, scientists realized that the way Jupiter's upper and lower atmospheric layers interact results in a vertical flow, something that also happens here on Earth. A Ferrel cell is a kind of wind pattern, and there are 2 of them on Earth. On our planet, there are what are called Hadley cells near the equator, which move warm air upward. Toward the poles, there are polar cells, which bring cold air downward. And in between, the Ferrel cells act like a buffer zone. They spin in the opposite direction to other cells, creating a zigzag pattern of wind traveling through each hemisphere. But the largest planet of the solar system has 8 such patterns. These cells align with the expected boundaries of what we might call Jupiter's version of Earth's Ferrel cells. And according to scientists, this is how Jupiter's iconic color bands form. On the gas giant, the wind patterns are different from Earth's, mainly because Jupiter doesn't have a solid surface. But researchers think they found something interesting a few miles below the gas giant's clouds that could act like a stable layer similar to Earth's surface. Based on computer models, something seems to be slowing down the winds in circular patterns on Jupiter. One idea of what that could be are really tall vertical versions of Earth's Ferrel cells. These cells could be affecting how the winds move and causing strange phenomena, like ammonia forming into slushy oval shapes, extending 60 miles deep into Jupiter's atmosphere. As ammonia rises, it gets colder and forms icy clouds in the higher parts of the atmosphere. Then, the air that's left sinks back down, but it doesn't have much ammonia left in it, which creates a kind of column where the ammonia is mostly at the bottom and less as you go higher up. An ammonia-water solution is also responsible for lightning, which mostly takes place near the planet's poles. And then, there are turbulent thunderstorms that sweep across Jupiter's vast atmosphere. Jovian storms are intense, and they may give rise to peculiar hailstones rich in ammonia, which scientists call mushballs. Mushballs on Jupiter are believed to form when thunderstorms lift water ice crystals upwards, reaching heights of over 16 miles above water clouds. There, they encounter ammonia vapor, which melts the ice and forms a unique solution of ammonia and water. The process happens at temperatures below -126 degrees Fahrenheit, where liquid water cannot exist, but the presence of ammonia acts as an antifreeze, allowing the formation of liquid droplets. Within these newly formed clouds, droplets of ammonia water liquid can collide with the ascending water ice crystals, electrifying the clouds and creating lightning. As the mush balls grow larger, they accumulate layers of slush and ice, becoming increasingly heavy. Eventually, they become too massive, plummeting deeper into Jupiter's atmosphere. There, they face warmer temperatures and evaporate. All this shows just how much more complicated Jupiter's atmosphere is compared to what we previously imagined. In the past, scientists have studied the most peculiar features on Jupiter, its colorful bands, the Great Red Spot, its dark and bright patches. But we know very little about what's going on inside of the giant, beneath its atmospheric cover. Gas giant planets probably don't have real inner layers as those common among Earth-like planets. It's just a slow transition from the atmosphere and to the planetary core. Let's imagine you fell into Jupiter. What would you see and feel as you descend into the clouds of the planet? Well, first of all, it's a gas giant, and that means you'd keep falling deeper and deeper without landing on a solid surface. But the free fall would feel so long, and it wouldn't be that long until you perish. Even before you get close to Jupiter, intense radiation would penetrate your suit, which would mean the instant end of you. So you'll need an advanced radiation-proof spacesuit that would offer some chance at survival in this unforgiving environment. On our planet, free-falling objects continuously accelerate by about 32 feet per second every second. As you descend to the top of Jupiter's atmosphere, your free-falling speed, something known as terminal velocity, would be about 2,000 miles per hour, much faster than a fighter jet on full afterburners. At one point, you would enter the area of ammonia clouds, where temperatures plummet to a bone-chilling minus 240 degrees Fahrenheit. Jupiter's clouds churn with intense winds, reaching speeds of up to 425 miles per hour, so you'd be dragged around like a leaf in a tornado. On top of that, the gas giant's upper atmosphere spins at 110,000 miles per hour, and at this speed, if you happen to collide with a dense gas cloud, it would be like hitting a wall. Later on in your descent, if you survive the previous obstacles, you'd see clouds changing in color. These clouds contain ammonium hydrosulfide and ammonium sulfide. They have a brownish tint, which would become more brown in color the deeper you fall. At first, the pressure around you would be bearable, even for somebody without a spacesuit, roughly what you'd experience 100 feet underwater here on Earth. Eventually, that pressure would reach 1,000 times the Earth's atmospheric pressure, but for now, you've reached clouds of water. Although a spacesuit can protect you from external pressure, it cannot prevent the physiological effects of breathing gases at high pressures. And at 10 times the Earth's pressure, breathing normal air is extremely dangerous because of oxygen toxicity and nitrogen narcosis. Oxygen toxicity happens when the body is exposed to high levels of oxygen for an extended period of time and at elevated pressures. Breathing air with elevated oxygen levels can lead to the production of what are called reactive oxygen species in the body, causing damage to cells and tissues. This can result in symptoms ranging from mild discomfort to convulsions and could have lethal consequences. Nitrogen narcosis happens when nitrogen gas dissolves in the bloodstream under high pressure, affecting brain function. Similar to the effects of alcohol or sedatives, nitrogen narcosis can cause impaired judgment, euphoria, and altered perception. But it can also progress to more severe symptoms, including confusion, hallucinations, or loss of consciousness. Both oxygen toxicity and nitrogen narcosis are influenced by pressure because pressure affects the solubility of gases in the bloodstream. As pressure increases, the amount of oxygen and nitrogen dissolved in the blood also increases. To avoid this, your spacesuit would have to adjust the air mixture you breathe to maintain safe oxygen and nitrogen levels, adding helium or neon to the mix. And this is just the beginning of your long descent into Jupiter. As you fall deeper and deeper, it gets darker and darker, all because of the increasing pressure. Visibility would be limited because of the dense and opaque nature of the gas giant's atmosphere through which light struggles to penetrate. As light enters, it becomes scattered and absorbed by the dense gases and particulates. resulting in a hazy and murky atmosphere. And even if your spacesuit is equipped with a powerful light source, it would still be difficult to see further than just a few feet. So you'll need to have specialized equipment, tools with sensors that can scan the environment surrounding you. If you somehow manage to survive the fierce pressures over 400 miles below Jupiter's atmosphere, you would enter a realm of the mighty gas giant that's never been explored before. Although no communication with the Earth or even a satellite orbiting nearby would be possible, all radio waves would become absorbed by Jupiter's dense atmosphere. The entire journey toward the gas giant's center would take over 20 hours, but halfway through, you would already be exposed to temperatures hot enough to melt tungsten, a greyish-white metal with the highest melting point among metals known to science. All the while, pressure increases drastically, so there's no way you could survive this. The increase in pressure would also act against your downward motion, slowing down your freefall. It's similar to trying to move through thick mud or syrup. The denser the substance you're moving through, the harder it is to keep moving quickly. So despite gravity pulling you downwards, the increasing density of Jupiter's atmosphere gradually slows your descent. Some 10 hours later, your body finally hits the central part of Jupiter, which is thought to be composed of metallic hydrogen. There, the temperatures are higher than the surface of the Sun, and pressures reach about 2 million Earth atmospheres. The atmosphere is so dense, it turns metallic hydrogen into a liquid. In environments like Jupiter's interior, where there's little to no oxygen available, your body would undergo a process called carbonization. Without oxygen to support the usual processes of decay or decomposition, the body's organic matter goes through a chemical transformation. It occurs at high temperatures and involves the breaking down of organic compounds into carbon-rich residues similar to charcoal. The immense pressure would exert a force equivalent to about 650 million pounds, pressing down on every square inch of your body, or the piece of charcoal that it's turned into. But let's imagine your body remains intact. It primarily consists of water, and water molecules have a strong hydrogen bonding, which resists external forces trying to push the molecules closer together. As a result, even under extreme pressures, water retains much of its volume and density, making it almost incompressible. At one point, the density of your body would match the density of the surrounding atmosphere. From now on, you no longer fall, and your body floats in place. Although we still don't know for sure what Jupiter's core is like, an alternative idea is that it's solid, almost like a rock, 14 to 18 times the mass of our planet. In the next few years, science will uncover more about the celestial gas giant, and perhaps these revelations will once again change what we think about gas giants and their place in the vast cosmos. Until that happens, we're left to wonder what mysteries the planet holds. A celestial marvel at the threshold between a planet and a star. Decades of extensive studies have demonstrated just how remarkably intricate Jupiter is. Just recently, 12 more moons orbiting the gas giant have been discovered. The total number of satellites around Jupiter is now 92, more than any other planet in the solar system. The latest moons discovered have sizes ranging from 1 to 3.2 kilometers. A majority of these moons have extensive orbits, with 9 out of 12 taking over 550 days to complete one revolution around the planet. Scientists believe that because these distant moons move in the opposite direction of Jupiter's rotation, they could be captured asteroids. It's been widely believed that Jupiter acts as a protective shield, safeguarding our planet from threats from outer space. In the past, astronomers have even suggested that this was one of the reasons life got a chance at evolving on Earth. But recent findings cast doubt on Jupiter's role as Earth's celestial guardian. Long-period comets, which originate from the distant regions of the solar system and take millennia to orbit the Sun, typically enter our vicinity. However, thanks to Jupiter's gravitational influence, most of these swiftly moving icy objects are flung away from the solar system before approaching Earth. So the chances of long-period comets colliding with our planet are extremely rare. Occurring over millions or even tens of millions of years, and Jupiter's presence plays a crucial role in shielding Earth from these potential impacts. However, the gas giant's gravitational forces have both positive and negative implications for life on Earth. On one hand, its immense gravity prevents nearby space rocks from accumulating and forming into a planet. This led to the formation of the asteroid belt, a collection of numerous small debris fragments scattered between Mars and Jupiter. But nowadays, the gas giant's gravitational pull continues to influence asteroids, causing some to deviate towards the Sun. This change in their trajectory increases the odds of collisions with Earth, and we've already witnessed it in the past. In 1770, Lexell's comet passed just about 1 million miles away from our planet, an extraordinary proximity on an astronomical scale. Scientists believe that this comet had initially come from the outer reaches of the solar system and had a close encounter with Jupiter that redirected its path towards Earth. After completing 2 orbits around the Sun, the comet returned to a point of close proximity to Jupiter 9 years later, which subsequently ejected it from our solar system. The Jupiter shield theory, supported by previous computer simulations, suggested that the gas giant ejects countless long-period comets out of the solar system. And this theory even predicted the comet Shoemaker-Levy 9 striking the 5th planet in 1994. But computing resources weren't as powerful as they are nowadays, and scientists had to make a lot of calculations. Today, we have data that includes a greater number of short-period comets and near-Earth asteroids that intersect with Earth's orbit compared to long-period comets, and new simulations demonstrate a different picture. Jupiter's influential gravity interacts with the asteroid belt, causing gravitational resonances that clear out rogue asteroids and redirect them inward. Collisions between asteroids can also contribute to this process by dispersing rocky fragments into resonant zones. The inner edge of the asteroid belt is particularly affected by a phenomenon known as secular resonance, which drives material into the inner solar system. Jupiter's current mass allows it to both redirect comets towards Earth, as seen with Lexell's comet, and effectively remove them from the solar system. If Jupiter had only 1/5 of its current mass, it would still destabilize comets, but lose the ability to remove many of them, leading to a higher impact rate on Earth. The frequency of impacts plays a crucial role in the long-term evolution of life on a planet. Earth's geological record indicates that an impact rate of 1 major collision every 100 million years provides enough time for the biosphere to recover and thrive. However, a higher impact rate, occurring every few million years, could devastate the planet, hindering the development of a new biosphere. Some scientists believe collisions with Earth is also how water was brought here. But what about water on Jupiter? Water vapor was first detected on Jupiter in 1995. This discovery was made by the Galileo spacecraft, which conducted extensive observations and measurements of the planet and its moons. The onboard instruments of the Galileo spacecraft, particularly the near-infrared mapping spectrometer, detected the presence of water vapor in the planet's atmosphere during its close flyby. But recent data demonstrates water makes up approximately 0.25% of Jupiter's atmosphere above the planet's equator. While this may not sound like a lot, it's actually an immense amount of water. Jupiter, probably the first planet to form in our solar system, contains a significant amount of gas and dust that didn't become part of the Sun. Knowing just how much water is locked up in Jupiter is crucial for scientists studying the formation of the solar system. In recent years, a team of researchers used telescope data to discover a substantial presence of water within Jupiter's famous Great Red Spot. Launched by NASA in 2012, the Juno spacecraft currently orbits the gas giant, taking close-up pictures of its clouds. Equipped with advanced instruments, the spacecraft has now revealed even more evidence of water on Jupiter. Because this massive gas giant holds more than double the combined mass of all the other planets in our solar system, even small fractions of water on such a massive planet would amount to a significant quantity, far exceeding the amount of water found on Earth. Water in the gas giant's atmosphere is also the reason why Jupiter, just like Earth, has its own mesmerizing displays of lightning 100 times brighter than terrestrial lightning and peculiar hailstones. Lightning has been detected in the planet's water clouds in the past, where water droplets collide with electrically charged ice crystals. But the Juno spacecraft has also spotted dim lightning at higher altitudes in the atmosphere, where the temperatures drop to approximately -87°C, too frigid for water to exist in its liquid state. So how does lightning happen under such conditions? The answer to the mystery lies in ammonia, a remarkable component in Jupiter's atmosphere that serves as a natural antifreeze. In the upper atmosphere, water ice crystals combine with ammonia vapors and melt. These water-ammonia droplets then collide with additional ice crystals from below, creating an electrical charge that generates lightning. Below the ammonia ice clouds, the ammonia water droplets undergo continuous growth until they become too heavy to remain suspended in the air and resemble large hailstones like we have on Earth. Scientists believe that these mushball-like objects descend deeper into Jupiter's atmosphere. But now, let's travel even deeper into Jupiter's innermost layers. Previously, it was believed that our solar system's giant worlds all have a rocky core. This was the accepted theory for a very long time, but recently, scientists have started to doubt this theory. Using Juno's orbit data, scientists are still studying how matter is distributed inside Jupiter, and recent discoveries have unveiled an unexpected mystery lurking within the gas giant's core. Jupiter's core has extremely high pressures, much greater than on Earth, and temperatures as hot as 20,000 degrees Celsius. To understand these conditions, scientists use powerful lasers to compress samples and mimic the planet's pressures in a laboratory. The Center for Matter of Atomic Pressures at the University of Rochester is at the forefront of this research. The density of materials in Jupiter's core depends on their composition and physical properties. And just recently, scientists have discovered that Jupiter's core is not as compact as they thought it was. Deep within its inner regions, only 18% of the material is rocky. Jupiter is predominantly made up of hydrogen, accounting for about 90% of its composition, along with roughly 10% helium and trace amounts of other elements. In the outer layers of this gas giant, hydrogen exists as a colorless and transparent gas, in the same form as it exists here on our planet. As you descend deeper into Jupiter, the increasing atmospheric pressure transforms hydrogen into a bizarre, dense fluid that conducts like a metal. So what is this substance? Approximately 10% of the way towards Jupiter's core, along its radius, the immense volume of hydrogen gas that forms the planet's atmosphere becomes compressed into a unique form known as liquid metal hydrogen. Liquid metallic hydrogen possesses properties similar to water, with low viscosity, excellent electrical conductivity, and efficient thermal conduction. Within Jupiter, this abundant substance transforms the planet into one huge generator. On Earth, elements exist as solids, liquids, or gases, depending on temperature and pressure. While hydrogen is typically a gas on our planet, it can be compressed and cooled artificially to become a liquid or solid. However, even in these states, hydrogen retains its non-metallic nature, poorly conducting heat and electricity. In contrast, metals excel at conducting heat and electricity due to their atom arrangement. Deep within the gas giant of our solar system, hydrogen undergoes extreme temperature and pressure, which allows for peculiar states including liquid metallic hydrogen. Hydrogen atoms under these conditions shed their electrons, resulting in a mix of free-floating hydrogen nuclei and electrons. This electron mobility resembles metal behavior. There's a theory that Jupiter's core might be filled with vast oceans of this substance, and based on previous estimations of the Jovian core's mass, it could be 12 to 45 times more massive than our planet. A 40,000-kilometer deep layer of liquid metallic hydrogen, combined with Jupiter's rapid rotation of about 10 hours, generates a colossal magnetic field that spans an astonishing distance of 725 million kilometers. This magnetic field stands as the largest in our solar system, and it contains mysteries of its own. Exploring regions more than 320 kilometers down into Jupiter's atmosphere, scientists have identified a newfound area known as the Great Blue Spot, not to be confused with Jupiter's Great Red Eye Storm. Researchers knew that the Jovian magnetic field was complex, but they had no idea just how weird it was. And it has something to do with the Great Blue Spot. The Jovian magnetic field is 20,000 times stronger than the Earth's magnetic field. But now, scientists have discovered that its strength is volatile. Unlike the Earth's dipolar magnetic field, the gas giant's magnetic field originates from a wide area in the northern hemisphere and re-enters near the South Pole. Researchers have also identified a concentrated region just south of the equator, the Great Blue Spot. Is like a second Jovian South Pole located near the equator. The colossal storm that's raged for centuries is probably caused by the presence of high concentrations of ammonia in the atmosphere. The intensity of the magnetic fields in the Great Blue Spot undergoes fluctuations of up to 1% per year, strengthening and weakening across different regions. By the end of the extended Juno mission in 2025, scientists will have ample evidence to evaluate their hypothesis. As research continues, we're going to encounter new mysteries about the gas giant. Since the Great Blue Spot and the Great Red Spot are located at the same latitude, it's possible the two phenomena are somehow connected. Gas giants are typically characterized by their high temperatures, especially in their upper atmospheres. In our solar system, there are two such giants, Saturn and Jupiter. However, Jupiter doesn't have a consistently high temperature throughout its entire structure. The solar system's largest planet is mostly known for its massive storm, twice the size of Earth, the Great Red Spot, but the gas giant has other spots too. The Great Cold Spot is nearly as large, and scientists have been observing this phenomenon for years now. At its largest, the spot is approximately 12,000 by 24,000 kilometers across. But unlike the famous red spot, this intriguing atmospheric feature stands out as a region of significantly colder temperatures compared to its surroundings, about 200 degrees cooler than the surrounding atmosphere. The Great Cold Spot is volatile, disappearing and reappearing from time to time. Scientists have discovered that this phenomenon's recurrence is triggered by the planet's auroras. Because of this correlation, the spot's age is about the same as the age of Jupiter's polar lights, which is in thousands of years. Jupiter's auroras, similar to Earth's, are produced by charged particles interacting with the planet's atmosphere near the poles. However, the gas giant's polar lights are more stable and intense, as they receive particles from both its moons and the sun. New findings indicate that these auroras transfer energy to Jupiter's atmosphere, creating a temperature difference between the upper and lower regions. This temperature contrast leads to the formation of a swirling vortex, resulting in a cooler patch that is distinct from the aurora and its surroundings. Earth also experiences similar effects. However, the combination of factors like Jupiter's rotation that helps retain heat in specific areas and the varying nature of these events makes the occurrence of polar lights on our planet less consistent. Another discovery made about the gas giant was that, contrary to common belief, Jupiter doesn't actually orbit the Sun. The center of gravity between Jupiter and the Sun does not reside within the Sun itself, but instead exists at a specific point just above the Sun's surface. In space, where a smaller object seemingly orbits a larger one, both objects actually orbit around a combined center of gravity. Consider Earth and the Sun, for instance. In this case, the center of gravity is so close to the center of the larger object that its impact is hardly noticeable. The larger object appears motionless, while the smaller object traces a seemingly perfect circular path around it. The same happens when the International Space Station orbits the Earth. Both the Earth and the ISS orbit around their shared center of gravity, even though our planet seems to be completely stationary, while the ISS appears to orbit the Earth in perfect circles. This principle generally holds true for most planets in our solar system. Even Saturn has negligible influence on the Sun's position in space. However, as the difference in mass between the two objects decreases, everything changes. In the case of Jupiter, its immense size causes the center of mass, known as the barycenter, to exist 1.07 solar radii away from the Sun's center, approximately 7% of a solar radius above the Sun's surface. This means that both the Sun and Jupiter orbit around this particular point in space. Our ancestors knew the monstrous size of Jupiter. The gas giant's mass is 2.5 times the total mass of all the other planets in the solar system, and 317.8 times the mass of the Earth. Jupiter's volume is 1,300 times larger than our planets. But today, we've advanced technologies that help us learn more about the gas giant than just size and mass. And astronomers pay a lot of attention to the study of Jupiter, as our planet's future depends on it. The latest data we have shows that, right now, something strange is happening with the planet. Jupiter is considered the super vacuum cleaner of the solar system by astronomers because of its immense gravity well and where it orbits in the inner solar system. The gas giant has taken some huge impacts from asteroids that could have hit Earth in the past, like Shoemaker-Levy 9, which slammed into Jupiter as it broke into pieces in 1994. But the planet's gravity isn't always protecting us. Along with Venus, it affects the Earth's climate. Every 405,000 years, gravitational fluctuations between Earth, Venus, and Jupiter bring us abnormally cold winters and hot summers. Droughts become severe and rains cause floods. Researchers say we're now somewhere in the middle of this cycle, and if something goes wrong on Jupiter, it could affect Earth in a big way. So what is the weird thing going on with Jupiter? For once, its most famous storm seems to be shrinking, and we have no idea how that will affect the planet. The Great Red Spot is a huge anticyclonic storm on Jupiter. The largest storms on Earth are more than 1,600 kilometers across, with winds reaching up to 320 kilometers per hour. But these hurricanes pale in comparison with the Great Red Spot anticyclone, which is about 16,000 kilometers in diameter. The gigantic storm is circling Jupiter at 650 kilometers per hour. Astronomers discovered the Great Red Spot in the 17th century, and scientists still study this phenomenon. The distinctive color of Jupiter's Great Red Spot has been a mystery for a long time. Some scientists believe the storm is colored by complex organic compounds. The whirlwind lifts them from the inside of the planet into the upper layers of the atmosphere. Others think the rusty color comes from sunlight splitting up different chemicals in the anticyclone's upper atmosphere. If so, the storm isn't actually very red at all, and what we might see is just a sort of sunburn at the top of it. Another interesting question is why the anticyclone lasts so long. Scientists have suggested it's because of Jupiter's composition, which is mostly hydrogen and helium. The gas giant has no solid surface to frictionally weaken the storm. On Earth, friction reduces the wind speed near the surface. This slows down storms. But other planets in our solar system aren't like the Earth either. Saturn, for example, isn't rocky, and storms there don't last this long. The biggest storm on Saturn, the Great White Spot, covers several thousand kilometers. You can see it through a telescope as a white oval. This spot appears every 30 years and then vanishes without any trace. The Big Dark Spot on Neptune, which was discovered in 1989, was also proved to be short-lived. The wind around the storm reached supersonic speeds of up to 2,400 kilometers per hour. The large dark spot was constantly changing its shape and size. With that much activity, the storm was clearly not going to subside, and yet, in 1994, it disappeared. But let's get back to the Great Red Spot. The Juno spacecraft passed over the anticyclone twice in 2019. It took images of the storm to help determine its nature. Using Juno's data, scientists compiled a three-dimensional model of Jupiter. It showed that the Great Red Spot extends much deeper than previously thought. On Earth, a storm of this size would rise above the International Space Station. Researchers say that, taken from above, the cyclone looks like a huge pancake, but a really thick one, going 500 kilometers deep into the clouds of Jupiter. This is 50 to 100 times deeper than the Earth's oceans. The storm is powered by atmospheric jets that go far deeper, about 3,000 kilometers. Scientists are still trying to unravel the mechanism behind how these jets move. So far, there's only one clue from the spacecraft data. atmospheric ammonia gas is moving up and down in the jets. This is very different from the way things happen on Earth. On our planet, atmospheric phenomena are largely driven by water, clouds, condensation, and sunlight. This is what we'd probably see inside the Great Red Spot if we could get there. The gravity there would be intense. The Juno spacecraft passing over the Great Red Spot was like driving a car on a road full of potholes. Radio waves reaching Earth were slightly compressed and stretched. Thanks to this effect, scientists picked up tiny tremors, 0.01 millimeters per second, and were able to calculate the gravity inside the storm. It turned out to be so strong, as if a mysterious planet was hiding at the bottom of the anticyclone. But of course, scientists didn't find any planet there, only a gas surface. Meanwhile, new measurements from the Hubble Space Telescope show that the storm has changed its form from oval to round and shrunk considerably. Previously, 3 Earths would fit inside the monstrous storm, but now only 1. Look at these Hubble telescope images from 1995, 2009, and 2014. You can see how the Great Red Spot has shrunk in just 19 years. So why is the storm on Jupiter shrinking? And do we have anything to worry about if the storm disappears? According to researchers, something in the planet's atmosphere is killing the storm. An unknown force is tearing apart the Great Red Spot. In May 2017, the Gemini North Telescope spotted a small hook-shaped cloud on the west side of the storm, and something else that looked like a wave peeling off its eastern side. The Juno spacecraft also took an image of red flakes flying away from the spot. Researchers confirmed that formations of various shapes actually detach from the Great Red Spot and scatter into space. These huge chunks, up to 100,000 kilometers in size, are about the size of Portugal or Iceland. Computer models show this is a very natural phenomenon for Jupiter's complex atmosphere. It may happen due to the convergence of the Great Red Spot and smaller storms. On Jupiter, anticyclones are attracted to other anticyclones, and opposites, such as cyclones and anticyclones, repel. The merging of anticyclones is a long process. In the beginning, a smaller storm becomes a small bulge closely adjacent to the larger hurricane. Then, the larger storm merges with the smaller one. But when anticyclones meet with cyclones, something different happens. A clockwise rotation of an anticyclone and a counterclockwise rotation of a cyclone first bring them to an abrupt halt. Then, the motion resumes with an unimaginable force and scatters the storms in different directions. A small anticyclone wouldn't merge with the Great Red Spot, but shatter into pieces instead. And these pieces of different shapes would then separate from the storm. This is what astronomers believe they are observing. And the Great Red Spot is still shrinking. According to scientists' calculations, it could disappear in about 20 years. Jupiter is unlikely to be affected, but there may be some irreversible processes that the storm was preventing. Only time will tell what will happen when the storm completely disappears. Based on data from the Hubble telescope, the average wind speed around the red spot increased by 8% from 2009 to 2020. And this means the anticyclone isn't losing activity and may increase in size again. Or it could be replaced by another storm. In 2000, 3 small oval white vortexes on the planet merged together. And at the end of 2005, a new hurricane turned red. Astronomers called it the Small Red Spot. In 2006, the Small Red Spot came into contact with the Great Red Spot. Because this was a slight collision, it didn't have any significant effect on the 2 whirlwinds. But how will the 2 storms get along in the future? To sort things out, NASA's mission Juno was extended for 5 years in 2021. The spacecraft will monitor mysterious polar cyclones, the planet's magnetosphere, and its incredible red storms. Jupiter continues to be studied by the Hubble and Webb space telescopes, as well as many ground-based observatories. Something recently happened that caught everyone's attention. NASA's Juno spacecraft is still out there wandering space, and for the first time since it was launched, it picked up an FM radio signal coming from Jupiter's moon, Ganymede. This is the same kind of signal that you would find here on Earth. In fact, we use this signal every day and know it as Wi-Fi. Did we just pick up an alien radio station broadcast from Ganymede? To figure that out, we need to know more about this icy alien world. Ganymede is the largest moon in the entire solar system. If it was orbiting the Sun, it would be a planet itself, being larger than Mercury. Although Ganymede doesn't have an atmosphere, it's the only known moon to have a powerful magnetosphere, which sometimes produce auroras that are affected by the moon's underground saltwater oceans. The rocking seen by the auroras gives researchers evidence that the underground oceans on Ganymede are possibly liquid and very salty, far saltier than the Earth's oceans. The FM signal that came from Ganymede originated from electrons in electromagnetic fields, a process causing the electrons to whirl and oscillate much slower than their spin rate. The Juno spacecraft detected the 5-second radio burst in late 2020, when the moon crossed a polar region of Jupiter where the gas giant's magnetic field interacts with Ganymede. So could there be life on Ganymede? Well, we know for sure the signal didn't originate from alien life. It's also very cold on Ganymede, with temperatures around minus 186 degrees Fahrenheit. However, during one of its flybys, the Galileo spacecraft detected a dense stream of atomic hydrogen escaping from the moon's very thin atmosphere. This means that there are large amounts of oxygen that's locked up or hovering over its icy surface. Atomic hydrogen is the lightest atom, and Ganymede has a weak gravitational field, so the hydrogen escapes and the atomic oxygen stays behind. Some researchers say that Ganymede could have as much oxygen on its icy surface as the Earth has in its atmosphere. So could Ganymede have everything for life to exist in its subsurface oceans? Some scientists think the pressure at the base of any ocean here would be so high that it would turn to ice. But a mission is needed to find out more. But this moon isn't the best candidate for life. In fact, there is another moon orbiting Jupiter that some scientists are calling the most habitable place inside our solar system. Europa is an icy white moon with brownish streaks on its surface and has an icy crust that could be from 2 to 20 miles thick. It's the smoothest surface of any other object in our solar system, and you wouldn't find any mountains or craters here. Underneath the icy surface would be a vast underground saltwater ocean, which could be twice the volume of those on Earth. Europa is very cold, with an average temperature of minus 260 degrees Fahrenheit, which keeps the icy crust as hard as granite. But could life still exist here? It's possible. At the dawn of the space age, it was thought that all life depended on the sun, and any object too far from a star would be a frozen ball of ice unable to support life. But finding thriving ecosystems at the bottom of Earth's oceans relying on hydrothermal vents changed all that. Now we know life is pretty tough, and it can survive completely isolated from the energy of a host star like our Sun. It's important to know this because Europa could harbor simple microbial life in liquid oceans underneath its icy crust, and this life could be surviving off the same kind of hydrothermal vents. So how do we know that Europa probably has liquid water needed for life to thrive? The Galileo spacecraft that flew over the moon in the 90s uncovered evidence of a vast, deep, dark, global subsurface ocean. Even though the moon should be a solid ball of ice, the water on Europa doesn't freeze completely because it's constantly churned by powerful tidal forces as the moon orbits around Jupiter, and at the same time, those tidal forces cause Europa's core to generate heat. Scientists are excited because this global ocean is thought to be in direct contact with surface ice and the moon's silicate mantle. This brings together everything needed for a habitable environment: liquid water, a source of energy, and a source of minerals and nutrients that life needs to flourish and survive. We know some bacteria or extremophiles like tardigrades can survive extreme environments, and just maybe Europa's hidden ocean could have these kinds of life forms. Between 2014 and 2016, researchers got evidence that there might be liquid water on Europa. Hubble Space Telescopic images showed evidence of huge geysers of water vapor, some 62 miles high, erupting from the surface over Europa's south pole. Although some researchers aren't sure, we're going to find out soon enough. NASA wants to send a probe to Europa by 2025. The spacecraft is called the Europa Clipper, and it will explore whether this icy moon has conditions suitable for life or not. The $2 billion solar-powered probe will fly by Europa 40 to 45 times using a number of high-tech instruments to study the moon's icy shell and the ocean that's underneath the surface. Will it find life? Only time will tell. And what about the Jupiter moon Callisto? Is it possible life could exist there as well? Callisto is the second largest Jupiter moon and the third largest moon in the solar system. It's almost the exact same size as Mercury, but with a surface temperature of -218 degrees Fahrenheit. It was once thought to be a dead moon because of its ancient cratered surface. In fact, it has more craters on its surface than any other object in our solar system. If you have many craters on the surface of any astronomical object, it means that geological processes are probably dead. But Callisto also orbits too far away from Jupiter to be affected by the gas giant's magnetosphere and heavy gravity. However, Callisto may also have an underground ocean, and the satellite's icy crust might be acting like a cosmic blanket, insulating this underground ocean. It's not clear whether this ocean could hold life because the surface is so old. The only way to find out for sure what's happening on these icy moons is to send a probe. NASA and the European Space Agency are building the Jupiter Icy Moons Explorer, or JUICE, which is planned to launch sometime in 2022 and begin a 7.6-year cruise to Jupiter, arriving sometime in 2029. We've all heard about the James Webb Space Telescope and the amazing potential it will have to find habitable exoplanets. But the JUICE probe is going to be carrying the most powerful scientific payload ever flown to the outer solar system, which includes 10 state-of-the-art instruments, plus will perform an experiment using the spacecraft telecommunication system with ground-based instruments. During the first part of its 3.5-year mission, the JUICE probe will make 30 observation overflights of the 3 icy moons Callisto, Europa, and Ganymede, studying them in close detail by examining their gravity, magnetic interactions, and checking to see if liquid water really does exist under the surface of each one. It'll then investigate whether these oceans might hold the organic components necessary for life, or even life itself. There's another interesting moon that's been grabbing the attention of researchers lately, but it's not in Jupiter's orbit. However, we think it's worth mentioning if we're going to talk about finding life in the solar system. In 2019, NASA revealed the ocean on the Saturn moon Enceladus contains the building blocks for life. This vast water ocean is about 6 miles deep and lies under an icy crust that's 19 to 25 miles thick. Images of huge plumes of water vapor erupting through cracks at the south pole of Enceladus were captured by the Cassini spacecraft and indicate there must be an underground ocean. These plumes were analyzed by the folks at NASA and found to contain water vapor, ice, salts, methane, along with simple and complex organic molecules, the kind of stuff normally found in living systems. The newest study of Enceladus shows the moon is more geochemically complex than previously thought, and that carbon dioxide is being controlled by chemical reactions on the seafloor of an interior ocean, boosting the chances of the moon having some kind of life. On Earth, oxygen-breathing creatures consume energy in organic matter like glucose and oxygen to create carbon dioxide and water, and oxygen-breathing microbes can metabolize hydrogen to create methane. NASA's Cassini's EON and neutral mass spectrometer detected methane, carbon dioxide, ammonia, molecular nitrogen, and molecular hydrogen in the plumes. And molecular hydrogen would indicate there is free energy available in the oceans of Enceladus. Cracks in the ice where the plumes erupt have temperatures warm enough that seems to show the ocean is being heated by the moon's core. These hydrothermal vents could be similar as the ones found on the Earth's oceans and are hotspots for life. A team of scientists now want to send a probe to the moon to find out. It's called Orbilander, which would cost $2.5 billion. The probe would orbit Enceladus for 200 days, which won't be easy considering Saturn's giant gravity field. Orbilander will fly through these plumes of vapor, which will then funnel into science instruments at high speeds. But this probe won't only orbit the moon, it'll also land on the surface, and so it will need to find the perfect place. Once the location is found, the probe will convert to a lander. 2 nuclear power sources will keep Orbilander running on the surface of the moon for up to 1.5 years while it sends data on what it finds back to Earth. Our solar system began as a disk of dust and gas some 4.6 billion years ago. The first planets to form were the gas giants Neptune, Uranus, Saturn, and Jupiter. Jupiter took shape about the same time as the rest of the solar system, forming around 4.5 billion years ago, its strong gravity pulling in massive amounts of gas and dust from the disk before all the other planets formed. It was the first and the largest. Jupiter is mostly made up of hydrogen and helium, about 90% hydrogen and about 10% helium, almost the same composition as our Sun, which is about 70% hydrogen and 28% helium. Some astronomers call Jupiter a failed star. However, the gas giant only has a mass of 1,000th that of the Sun. Jupiter just isn't massive enough for gravity to trigger nuclear fusion. The beautiful whirling clouds and storms that you see in images, the layer resting on the surface known as the troposphere, are about 31 miles thick and are made up of ammonia, ammonium hydrosulfide, and water, which form the distinctive red and white bands. When you look at Jupiter, you probably think that it must have a solid surface. The fact is that Jupiter doesn't have a true surface. It's mostly swirling gases and liquids, and if you sent a spacecraft there, it would have nowhere to land. But just because the spacecraft wouldn't have a place to land doesn't mean it would fly right through Jupiter's atmosphere and come out unharmed through the other side. This is because extreme pressures and temperatures deep inside the planet would crush, melt, and vaporize any spacecraft trying to fly into the planet. But we've sent spacecraft to orbit and explore the planet. The $1 billion Juno probe, the farthest space probe ever to be powered by solar arrays, was launched towards Jupiter on August 5, 2011, and arrived in orbit around the planet on July 4, 2016. And what we've discovered and learned about Jupiter is incredible. The newest discovery using data collected from the Juno spacecraft found that the colorful stripes of swirling gas and dust you see in Jupiter's atmosphere were found to run 1,800 miles deep and hold so much gas that the mass is about 3 times that of the entire Earth. These belts of wind flow at speeds of 223 miles per hour and disrupt how mass is spread across the planet. It was also discovered that Jupiter's atmosphere is rotating differently, with zones and bands rotating at speeds that are different by up to 328 feet per second. Those bands on different colors you see are actually traveling in opposite directions. Lighter bands move in the direction of Jupiter's rotation, circling the planet faster than it spins, and the dark-colored bands move slower in the opposite direction and take longer to move around the planet. So how does a giant ball of gas floating around in space stay together and form a planet? The Jovian magnetosphere is the cavity created in the solar wind by Jupiter's powerful magnetic field, ballooning 600,000 to 2 million miles and tapers into a tadpole-shaped tail extending more than 600 miles behind Jupiter. This magnetosphere is the largest and most powerful of any planetary magnetosphere in the solar system. Jupiter's magnetic field is generated by electrical currents in the planet's outer core, which is composed of liquid metallic hydrogen. This magnetic field was found to be almost 20,000 times as powerful as Earth, and rotates with the planet sweeping up particles that have an electric charge. The electromagnetic storms they generate are so strong that they can be heard by amateur radio operators on Earth, beamed towards us by plasmas and magnetic field lines. These signals are sometimes even more powerful than radio signals from the Sun. This magnetic field traps swarms of charged particles and accelerates them to very high energies, and creates intense radiation that bombards the innermost of its 67 confirmed and named moons, and would destroy anything that got close. Speaking of Jupiter's moons, scientists have recently discovered an FM signal emanating from one of Jupiter's moons, Ganymede. If you want to see a video about this mysterious signal and Jupiter's giant moons, let us know in the comments. By now you may be wondering, does Jupiter have a solid inner core? Studies have found the planet's interior moves as a single body and behaves as if it were a rigid solid, despite its fluid nature. For now, we simply do not know if Jupiter has a solid core or not, but the Juno spacecraft should be able to help discover this, and what the mass and makeup of this solid core is, if it exists. We do know that at Jupiter's core, whatever it's made of, the pressure is about 100,000 times the pressure on Earth. The Great Red Spot is one of the most iconic features of the planet. It's a massive storm the size of the Earth that's been raging since it was first sighted in 1831. Trapped between two jet streams, it's called an anticyclone that swirls about a center of high atmosphere pressure and rotates in the opposite direction that hurricanes do on Earth. It's the largest storm in the solar system, with wind measured around 400 miles per hour. Compare that to the fastest wind speed ever recorded on Earth of 231 miles per hour. One day this Great Red Spot could end up disappearing completely, and scientists say that it's been shrinking since the 1800s, and may only last another 20 years. NASA's Juno spacecraft was able to snap incredible images of the planet as it passed at 5,600 miles above the giant red spot clouds in July 2017. One of the amazing things that was discovered is that deep in the atmosphere, pressure and temperature increase greatly and compress the hydrogen gas into a liquid. This gives Jupiter the largest ocean in the solar system, which is made of hydrogen instead of water. Juno also grabbed some spectacular images of the gas giant's poles, discovering another incredible wonder of the planet. At the North Pole of Jupiter, a huge persistent cyclone is visible, and encircled by smaller cyclones ranging in size from 2,500 to 2,900 miles. On Jupiter's South Pole, the same thing was discovered as Juno did a flyby, and using infrared cameras imaged a cyclone the size of the entire USA, with 5 other cyclones swirling around it in a geometric pattern, which also rotate counterclockwise. The NASA Galileo spacecraft was likely the first to discover these hotspots when it accidentally flew through one on its way to a planned demise to the surface of Jupiter. When the spacecraft was almost out of fuel, NASA deliberately sent the craft on a no-return plunge into Jupiter on September 21, 2003. This was done to protect the moon Europa, which some say has a subsurface ocean that could contain life. It's worth mentioning that we probably should be thankful for the planet Jupiter's size and the powerful magnetic field that it generates, because it's possible that Jupiter has saved the planet Earth from certain doom. People were laughing at the prospect of an asteroid or comet hitting the Earth in the late 80s and early 1990s, but then something happened that would quiet that laughter. The comet Shoemaker-Levy 9 was discovered by Carolyn and Gene Shoemaker and David Levy on March 18, 1993, using the Schmidt telescope at Mount Palomar. Scientists calculated the comet was originally 1 to 1.2 miles wide. However, tidal forces from Jupiter's powerful gravity had broken the comet into more than 20 pieces as it made its close approach to the planet sometime in 1992. But the biggest revelation was scientists saw that the fragments were going to smash into Jupiter, and luckily for NASA, its Galileo orbiter was still on its way to the gas giant. Many Earth-based telescopes and orbiting spacecraft such as the Hubble telescope all were focused on the incredible event that was about to happen. The fragments of the comet were lined up like a freight train and collided with Jupiter's atmosphere, unleashing the force of 300 million atomic bombs. The fragments created huge dark spots in the clouds that measured 1,200 to 1,900 miles and heated the gas giant's atmosphere to temperatures as hot as 53,000 to 71,000 degrees Fahrenheit. If a comet of this magnitude hit the planet Earth, the results would be devastating, with impacts sending dust and debris into the sky, which would cool the atmosphere and absorb sunlight and envelop the entire planet in darkness. This historic Jupiter comet impact is what led to planetary defense. But fear not, this type of collision was very rare, and scientists say probably only occur every few centuries. Or do they? On August the 7th, an amateur astronomer was looking at Jupiter through his telescope when he captured an asteroid colliding with the atmosphere of Jupiter, creating a white flash visible in the clouds. Some scientists say these impacts are inevitable, with the amount of objects floating around in space and Jupiter's massive gravity tugging on anything that gets close to it. We could say that Jupiter's like Earth's big brother and likely protecting us from asteroid impacts. We've learned some new things about Jupiter and how its layers of atmosphere are made up. And we've also been able to image the planet in striking detail, piecing together images captured at the perfect moment for clarity called lucky imaging. The highest resolution image of Jupiter ever seen has been created in thermal infrared light. In the photos you can see the familiar banding. Bright regions are clear air, where heat from inside the planet can leak out, and darker regions are where the thick clouds block the heat from escaping. This proves that the interior of Jupiter is very hot, heat left over from its formation billions of years ago. When taking a look at Jupiter through the Hubble telescope, what you see is sunlight reflecting off the cloud tops. With these amazing images, we're learning more and more about Jupiter every day. And we're not done yet. Juno is still on its mission, and only about 1/3 through its planned mapping of the planet. And there are still reasons to believe that Jupiter may have a rocky center that's enveloped in a layer of metallic hydrogen. We're definitely going to get more incredible images of Jupiter coming soon, and we're about to unlock the mysteries of the biggest planet in the solar system. So make sure to stay tuned here to see the latest stunning images of Jupiter.